Welcome friends. In today's lecture we are going to discuss metal forming, and specifically after discussing the types of metal forming processes, we will start the rolling operation and we will discuss rolling operation in details. So what is metal forming? Metal forming is a manufacturing process in which desired shape and dimensions are obtained through plastic deformation of material. What is meant by plastic deformation? I have already discussed all these things in previous lecture. You can see the lectures of strength of material. We have already covered 4 subjects with SOM, then engineering drawing, after that machine design and metrology. This is our 5th subject, which is manufacturing processes, and in that we have started metal forming processes, and first topic is rolling. So in short, I will tell what is plastic deformation. If you will see the stress strain curve in strength of materials, then there is a particular zone. For your information, I will draw short figure, small figure here. Let us say this is a stress strain curve for steel. This much portion from this origin to this, it is the elastic portion, and the deformation which is there in this region is called the elastic deformation. After that you will see some another shape like this. Here will be there will a elastic point. After that there will be plastic deformation star, and there will be some plastic deformation points, and ultimately here at the last you will get the ultimate strength, or the, in case of if it is a hard material, you will get ultimate point, and otherwise you will get some, in case of soft material, another points. I have already discussed different points. What is the plastic point 1, then plastic deformation point 2, and ultimate deformation or ultimate point. Why this stress strain curve is plotted in this way only, not stress versus strain. I have already covered these things. You should go and watch previous lectures of strength of materials of mine. So our metal forming is the manufacturing process in which desired shape and dimensions are obtained through plastic deformation of material, and this plastic deformation can be achieved by different processes like rolling, or there may be a, what I can say here, I have listed all the operations: extrusion, forging, drawing. What is mean of forging? If you are applying load by hammer, in that case it is called forging, or it also includes the heating up to, what I can say, the recrystallization temperature. We will discuss what is the recrystallization temperature and all in this lecture itself. Rolling we will discuss in detail here itself, and soon we will start rolling, drawing, all these operations for wire and tube making. Very first we will define what is the difference between the plastic deformation in case of if there is a sheet metal operation and other operations. If the volume to surface area is high, let us say this cube is there. Here you can see at the bottom, this is a cube. Then the volume of this particular object and ratio of this volume to the surface area of this object itself, if it is high, then we will not call it as a sheet metal. For calling sheet metal or any sheet metal operations to perform or use any sheet metal operation in the manufacturing process, we will first find the volume to the surface area ratio. If we found this ratio lower, then we will perform sheet metal operations. And again, sheet is again defined in different way, whether it is called sometimes plate or sheet or strip. If the thickness of this, let us say any object having volume to surface area ratio very minimum, in such case, if the thickness is greater than 6 mm, then we will call such an object as a plate. If the thickness is lesser than 6 mm, in these two cases, either it will be called as a sheet or strip. Here, just the difference is that if width is higher than the 600 mm and thickness is again lesser than 6 mm, then we will call it as a sheet. And for the same thickness, if let us say this is a sheet, and if you cut this sheet into different parts, let us say like this, okay, then what will happen, this width will reduce, and in such case such metal part will be called as a strip. Okay, provided thickness should be less than 6 mm. Now, what is recrystallization? If let us say we are applying load on a particular material with a hammer, then what will happen? There will be deformation at particular point, and due to this deformation there will be hardening of the same material, and at one point you will find that there will not be further deformation because of hardening of that material. And why it happens and how we can solve that problem of further deformation by using recrystallization temperature or heating up to recrystallization temperature. We have seen that up to particular limit, if we apply load on a metal, then there will be little bit of hardening, even though its strength will increase, but deformation will not be there. Why it happens? Here in this figure you can see, if you will see a metal part initially before the working, cold working means if you are heating a material up to lesser than recrystallization temperature. What is the recrystallization temperature? We are going to discuss. Let us say for steel it is 723 degrees Celsius, and I am heating a particular material for 500 degrees Celsius and applying load and deforming it. Then we will call it as a cold working. So before this cold working, if you will see a specimen of particular metal under the microscope or electron microscope, you will see such type of grain structure. Different grain structures will be there in the same material, and these dark blue lines are nothing but the grain boundaries. When we apply force or loading, what happens? These grain boundaries come closer due to deformation, and at one point they will come closer in such a manner that no further, let us just a minute. This was some technical glitch. The headphone call also. Okay, I'm back. I'm audible and visible properly. Yeah. So I was discussing about the these grain boundaries will come closer to each other, like very closer. So there cannot be further movement of these grain boundaries. Let us say an example of traffic signal. If there are the traffic signals are not working, let us say, then what will happen? All the people will come from all the directions. Let us say if it is a T point or a square, then what will happen? All the people will get stuck with their vehicles, and no further movement can be possible in such a manner. So To solve this problem, what we will do, we will heat the particular material up to the recrystallization temperature. After cold working procedure, here you can see the grain boundaries come closer. Here you can able to see more grain boundaries than this figure. That means it came closer to each other and no further movement of the grain boundaries is possible. So what we will do, again we will heat this material up to the recrystallization temperature. Then what will happen, like as soon as the traffic signals work, there will be a space created. Because of this heating, there will be a stress relieving process will occur here, and that's why what will happen, their grain boundaries will adjust themselves so that there can be a further deformation. Again we will heat above the recrystallization temperature. Let us say we are heating it. Then you will see a uni-axed grains. That means the what I can say, grain sizes of the all these grains will be similar, or there will be an average diameter to all the grains. Equiaxed grains means grains of equal average diameter. Here you can see near about the diameter of all the grains is nearly same, right? And again after further heating, what will happen, the grain growth will be there, and the grains will be so larger, and again if you will continue heating, the material will get converted into a liquid form. So in such these two steps, let us say after recrystallization temperature, there will be a decrease in the what I can say, strength, so that there will be a maximum ductility. Material can be easily deformed because of this heating process. So because after recrystallization temperature, the grain boundaries will get direction or space for further movement, so that they can adjust themselves for the deformation process. And what the things will happen at the recrystallization temperature, new set of strain-free equiaxed grains will be formed. There will be stress relaxation and equiaxed grains will be formed. So stress-free equiaxed grains will be there. That means having average diameter of all grain equal to particular average value. Average value of grains will be similar. Let us say within particular range. Let us say 1, 2, 3, like this. Ductility will increase, toughness will increase at this particular temperature, right? And strength will be decreased. So if the working temperature is less than recrystallization temperature, we will call such working process as a cold working. It doesn't mean we are working below the room temperature or at -degree or negative degree temperatures. Recrystallization temperature, if it is not achieved, then up to that temperature, all the working processes called as cold working processes. And after that, if working temperature is greater than recrystallization temperature, it is called as hot working process. Now, if it is a alloy, let us say it is a alloy, then what will be the difference in pure metal and alloy? Pure metals will have recrystallization temperature nearly up to the 30% of their melting point. Let us say for steel, we assume that 100 and 1500, let us say that melting temperature of steel, then 0.3 times, that means 30% of this melting temperature, there will be a recrystallization temperature. Not exactly, but up near about that. It will be different for different materials. Again, it also depends whether there is a alloy or a pure metal, as steel is a alloy of let us say carbon and ferrous iron. So for that, recrystallization temperature will be nearly 50% of the melting point. Here you can see 723 is nearly 50% of the 1500 degrees Celsius. That means 1500 degrees Celsius for steel. It is a approximate value, not the same always for each case. Now, from here we are going to start our rolling process. Here, how rolling is done and what is the purpose. You can see in this figure, this is a previous sheet metal. If you want to reduce the thickness of this sheet metal as well as by keeping the volume same for the this object, it is possible by rolling method or rolling process. What happens in this rolling process? Two rollers are kept one over the other, and in between, like a sugar cane juice machine, a metal is forced from the backward side, and it is pulled out of these two rotating rollers. It is not always necessary to push it from the back side. If particular coefficient of friction is provided between this roller and the sheet metal, then there may be a self rotation or self rolling can be possible. We will see all these things in detail one by one. Even though you can get a different width by keeping the not only by keeping the width constant, you can do rolling in both way. If you want to keep the same width, then you have to again provide two rollers, let us say in this axis. This is the axis of horizontal rollers. Then vertical rollers should be kept here at both the ends of the plate, and which will what will they do? They will resist the increase in the width. Here I have drawn that figure. Let me show you where it is. Okay, I will draw it for you if not drawn earlier. Here will be some rollers will be there, right? Let us say one roller will be here. I'll use different color. Yellow. Let us say here is one roller, small roller, and on the another side there will be another roller again, to avoid the deformation in this direction of width. Okay, so that we can get the plate or sheet or strip with same width, just the length will be increased and volume will also be again same. Like here, W is the width, H1 is the height. Final initial volume and final volume will be same. So you can see here VI, we can equate VI equal to V2. You know that volume is length into breadth into height. L1 B1 H1 is equal to L2 B2 H2. In case if V is kept constant, we will get L2 equal to L1 into H1 by H2. Here you can see L2 is greater than the L1, and that is why we are doing this operation just to reduce height and increase the length by keeping the volume constant. Let R is the radius of roll, this capital R. Delta H is the draft, that means the change in the initial height and the final height, delta H. So let us say H1 is the initial height and H2 is the final height. So from this equation we can also get H1 is equal to delta H plus H2. That means both are equal. In this figure you can see here it is drawn A, C, then B point is this. Here I have drawn it separately for your convenience. This complete O to A distance is R. Again O to B is also R. And here you can see this much distance is delta H by 2. So this CB is delta H by 2. And if complete is R, then if we will subtract R from this delta H by 2 from the R, we will get R minus delta H by 2. This is the difference between point O and C, that is distance OC. So OC will be, here I have written it, OB minus CB, that is R minus delta H. And this theta is the angle of bite or bite angle, which we obtain from the point of contact between the roller and the sheet up to this point only. That means the exit plane. This vertical plane we can call it as exit plane, which is perpendicular to the screen, let us say right now. Now in triangle OAC, if you want to get the value of theta, you can use trigonometry formula. Cos theta is equal to OC by OA is equal to R minus delta H by R, so delta H by 2 divided by capital R. So by equating this equation, transferring this R to this side, we are getting R cos theta is equal to R minus delta H by 2. And delta H by 2 is equal to, if you will take R constant, so you will get R in bracket 1 minus cos theta. By transferring this 2, we are getting twice R, 1 minus cos theta is equal to delta H. Okay, so delta H is equal to, you can keep instead of twice a diameter of the roll, D minus D into 1 minus cos theta, right? So we will use the delta H formula whenever we require in numerical, that is diameter of roll. Now roll sheet contact length, what will be that length? Here in the figure you can see this much is the contact area length. So we will obtain this length from this figure itself. How? We will again use the trigonometry. Theta is equal to arc upon radius r. So arc length is L. Here we will get L is equal to r theta. This theta will be in radians because it is not associated with any trigonometric function. Whenever there will be is only theta without any trigonometric function, then that theta will always be in radians. Here self entry, which I was talking about, if you don't need any force from left side or from the entry side to continue the operation with the help of only rollers, then in that case mu should be greater than the tan theta. Theta is the bite angle. This is the condition for self entry. Not if it is not greater than or equal to the tan theta, then we need to apply force from the entry side on the sheet or plate. So maximum possible draft in single pass, that means how much reduction will be there, maximum reduction, that will be delta H, can be calculated from this empirical formula. This is obtained from experiments and all, we need not to derive it. as if you are uh, preparing for any exam like GATE. So they will not ask. If you are preparing for ESE or engineering services, then it may ask. So if you want, you can go through both. Delta H is equal to mu square R. Anyway, I think this is the empirical formula derived from the experiments. Question 1 is equal to what it saying that we have given the roller diameter and reduction in area is given by 10%. Then that means the new area is 10% of the initial area. Final area is the 10% of the initial area. You can also write AF, that is final area, is equal to 0.9 times, that means 90% of the initial area. And what we have to calculate? We have to calculate angle theta. Whenever possible, use this angle formula. Delta H is equal to D into 1 minus cos theta. Another formula is there. You should not use. We will derive it in few slides. Next few slides. So look at here. We have the relation AF is 0.9 times the AR. Putting the value of area, width into the height, that is final width into final height, and initial width into initial height. Initial values are given. Here we are getting delta H is equal to 9 millimeter. Sorry, H2 is 9 millimeter. So H1 minus H2, delta H 10 minus 1. It will be 1. So delta H we will equate with the D into 1 minus cos theta. From here we are getting theta right angle is equal to 3.95 degree. Now question 2 is D equal to 600 millimeter. Roll diameter is given. Coefficient of friction between roll and plate or sheet is given. And initial height is given equal to 6 mm. And we have to find the minimum possible thickness in one part. Right. So this is formula given. Delta H is equal to mu square into R. As I have told you, if you will use this formula, you can even use if you have the value of theta, that is 1 D into 1 minus cos theta is equal to delta, that also. If not given and only mu is given, you have to use this same formula. Mu square is equal to R is equal to delta max. We have given H1 value and this is, let us say, H2. Right, final thickness, final thickness or height you can say. Here we are getting H2 is equal to 3 mm. This is in the only single pass. So this much maximum or minimum width can we get, not more than that. Even though because of hardening, which I have told you, there will be a strain hardening due to deformation. If you want to reduce it, if you will reduce the distance between the two rollers, let us say, and you forcefully try to do, rollers may get damaged, but there will not be further reduction in the thickness of the plate. For that, you have to heat material up to recrystallization temperature, and then you can reduce the height or thickness in single pass. Or without retreatment in single pass, you cannot reduce the thickness of the plate more than this 3 mm for this example. Here I have shown you the exit plane. This vertical yellow line or shaded portion is the area where there will be a force will be experienced, and the very first dashed line, this dotted line, you can see it is the entry plane. The middle one is the neutral plane where there will be a velocity of velocity of roller, right? Initial velocity will be vi, final velocity will be vo. Initially velocity will be lesser, and at the end velocity will be higher. So there will be a slip in between roller and plate in this region, except at the middle plane. These planes are shown by dotted lines. That means the plane are perpendicular to this figure on the screen. Okay, this blackboard. VR will be given by pi dn by 60, and where n is the revolutions per minute. Now, before neutral plane, the velocity of sheet will be lesser than the velocity of roller, and after neutral plane, that is the middle plane, velocity of sheet will be greater than the velocity of roller, right? So there are many things here which we have to explain, and we will solve few examples also. What I will do, I will explain this phenomena only, how there will be change in the velocity, what will be the forces. The remaining portion we will discuss in next lecture. I think you have got this. There is particular difference in the velocity. So you may have solved or studied this example. If there is a change in the velocity, relative velocity will be there, let us say, then how will be the frictional forces, and what will be the difference in the what I can say, if the particular surface is stationary and another surface is moving, then what will be the frictional force. So all these things we will discuss in next class. Till then you can enjoy this lecture or previous lectures for strength of material, because it is necessary to understand the stress strain curve and related things in this manufacturing processes, which will be helpful. So I advise you people to go and see the lectures of strength of materials, at least the stress strain curve. So it will be easy to you people to understand this phenomenon in the manufacturing processes. Thank you for watching this video. Remaining portion we will complete in next lecture. So keep us following, like, share and subscribe this channel. Thank you once again for watching this video. Signing off for the day.